Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.5. Continuity.
Lesson 4. Continuity of trig, exponential, and log functions. Part 1. Okay, great. So we've talked about these specific types of functions, polynomials, rational functions, root functions, and we've talked about combinations, adding those, subtracting those, multiplying those by a constant, multiplying two of those functions together, and dividing two of those functions. So we now know where those types of functions are continuous and where they are discontinuous, but there are some kinds of functions that we work with frequently that we have not discussed the continuity of yet. And one of those types of functions that's left for us to talk about are the trig functions. And we might want to ask, where are things like sine x or cotangent x or secant x, where are those functions continuous and where are they discontinuous? So let's talk a little about the continuity of cosine theta and sine theta to begin with, and then we'll talk about the other four trig functions. So I'm going to go ahead and look at this in a rather intuitive way. It is possible to rigorously prove where cosine and sine are continuous, but we're going to do this in kind of an intuitive way. I think it will be quite a bit quicker. And I want you to think about the unit circle, and remember, by the unit circle we mean the circle that has radius 1. You notice this radius here is marked with a 1 and centered at the origin. And the unit circle is particularly simple, simplifies our calculations of cosine of some angle theta and sine of some angle theta. So theta, as usual, is going to be an angle whose begins on the x-axis, whose beginning side is on the x-axis and whose terminal side is somewhere up here, and this terminal side will intersect with the unit circle at some point, and I've designated the coordinates of that point x, comma, y. So x, y are the coordinates of this terminal point on the terminal side of our angle theta. Notice that means that if we drop a little perpendicular to the x-axis, that this distance right here is really the same as x. It's how far over I have to go to get to this point, x, comma, y. And this height right here is really equal to y. It's how far I have to go up to get to my y coordinate on my circle. Well, remember the definition of cosine theta. It's the adjacent side over the hypotenuse in our little right triangle that we've drawn here. And what is the adjacent side? The adjacent side is x, and because this is the unit circle, the hypotenuse has length 1. So it's x divided by 1, or simply x. What does that mean? That means that whatever point the terminal side of my angle intersects the unit circle at, the x coordinate of that point is exactly equal to cosine of my angle, theta. So x is the same thing as cosine theta. This distance right here in my little right triangle, the adjacent side, is cosine theta, as long as I'm dealing with a unit circle and this hypotenuse is equal to the number 1. In a similar way, we can find sine of theta. Sine of theta, remember, is the opposite side in our right triangle over the hypotenuse. So that would be y over, and our hypotenuse is again equal to 1 because it's a unit circle. So sine of theta is equal to y. So the y coordinate of this point where my terminal side of theta intersects the unit circle, the y coordinate of that point is the same number as sine theta. Or another way to say the same thing is that the height of this right triangle here is the same thing as sine of theta. Okay, well now I'm going to ask you this question down here. If we change theta by a small amount, and here you notice that I had some angle theta here, and now what I'm doing is I'm increasing theta by a little bit. This brown line represents the terminal side of the old theta, and this green line here is going to represent the terminal side of the new theta. The question is, if we change theta by some small amount, what happens to the x and to the y? Remember that x is the adjacent side in this little new green right triangle that I have here, and y is really the height of this new triangle. And I guess what I want to get across is that if we change theta by a small amount, then the x is going to change by a small amount. Here was the old x for the old theta, and here's the new x for the new theta. It looks like it's slightly smaller. And the y is going to change by a small amount. Here's the old height in the old theta. Here's the new height in the new theta. It looks like y has gotten a little bit larger. But the important thing is that if we change theta by a small amount, x and y will also change by a small amount. In other words, x and y won't abruptly change and have like a totally different value. As we change theta by a small amount, x, it looks like shrinks by a small amount, and y, it looks like expands by a small amount. So as theta changes by some tiny amount, x and y also change by some tiny amount. So as theta changes, x and y will change in a continuous way. They won't suddenly jump to some completely different value. They will change in a slow and continuous way. So if we change theta gradually and continuously, x will change gradually and continuously, and y will change gradually and continuously. But remember that x is cosine of theta if we're talking about a point xy on the unit circle, and y is sine of theta. That's what we set up here. The y coordinate is the same number as sine of theta, as long as we're talking about a point on the unit circle, circle of radius 1. So what have we just said? We've said that as theta changes, x, which is the same as cosine theta, changes in a continuous way, and y, which is the same as sine theta, changes in a continuous way. So these things, cosine theta and sine theta, change in a continuous way as theta changes. So what does that ultimately mean? That means that cosine theta and sine theta are continuous functions of theta. As we change theta by a small amount, cosine theta and sine theta change by a small amount, so they change in a continuous way as we change the value of theta. So cosine theta and sine theta are continuous functions, and they're really continuous functions of theta over their whole domains. And remember that cosine theta and sine theta are defined for every real number theta. Now, oftentimes we use theta for the angle when we are talking about defining cosine theta and sine theta as the x and y coordinates on the unit circle. We don't have to use theta as the argument, as the input into our function. We can use any letter that we want to. So just notice you could also say cosine of x. Here we're using x in a different way than we did up here. We're just using it as the input into the cosine function. And sine of x are continuous functions of, and instead of theta, we could have just written an x there. So we're more used to thinking of the input into our functions as x than we are as thinking of the input as theta. So we can say cosine x and sine x are continuous functions of x, and they are continuous everywhere. They're continuous on the entire real number line from minus infinity to infinity. So just like polynomials are everywhere continuous, we can say cosine x and sine x are everywhere continuous. Okay, well, let's go ahead and look at the next page. So we've talked about 2 of the trig functions, but you may remember that there are 6 different trig functions. However, cosine x and sine x are rather important trig functions because all of the other trig functions can be defined in terms of them. So, for example, let's think about tangent x, and remember that tangent x can be defined in terms of cosine and sine. Tangent x is defined to be sine of x divided by cosine of x. And we might ask then about the continuity of tangent x. Where is tangent x continuous? Sine x is continuous for all real numbers x. Cosine x is continuous for all real numbers x. But what about tangent x, which is really the quotient of these 2? Well, now we can employ that theorem that we talked about. If we think of sine of x as our f, and cosine of x as our g. Remember that that general theorem that we talked about 2 pages back said that f over g is continuous everywhere at every x, that f and g are both continuous at, except where g is equal to 0. So maybe I should write f of x over g of x is continuous everywhere except where g of x is equal to 0. So since sine x is continuous everywhere and cosine x is continuous everywhere, f of x over g of x will be continuous at every single value of x, with the exception of places where the denominator is equal to 0. Those values f over g, in other words sine over cosine or tangent x, will be discontinuous. So the only kinds of values that we would have to worry about are values where the denominator, namely cosine of x, is equal to 0. So we have to ask ourselves, for what values of x, what real numbers x, is cosine of x equal to 0? And to get the answer to that, one way to do it would be to think about the unit circle again. So one way to do it is to consider the unit circle. Remember, that's a circle that's of radius 1 and centered at the origin. And remember that we said that cosine of x is exactly the same thing as the x-coordinate of any angle that terminates on the unit circle. We're looking for places on the unit circle, points on the unit circle, that would have an x-coordinate of 0. So where would the x-coordinate be 0? That would be at points like this one, at points corresponding to a terminal side of an angle of pi over 2, or 90 degrees. Cosine of 90 degrees, or cosine of pi over 2 radians, is equal to 0. And that's because this point has an x-coordinate, it's point 0, 1, and what we care about is that the x-coordinate of that point is equal to 0. The x-coordinate of that point is the same as cosine of this angle, pi over 2. So when x is equal to pi over 2, cosine of pi over 2 would be equal to 0. Well, where else do we have a point on the unit circle where the x-coordinate is 0? Down here at 3 pi over 2 radians, that would be 270 degrees. I would again have, see, I have the point 0, -1. I would again have an x-coordinate that's equal to 0. Cosine of 270 degrees is also equal to 0. So when x equals pi over 2, or when x equals 3 pi over 2, and remember that we are allowed to go around the circle more than once, so the next place that I would end up getting a point whose x-coordinate is 0 would be if I go around 360 degrees plus an additional 90 degrees. So that would be, let's see, 360 plus 90 would be 450 degrees. Cosine of 450 is also equal to 0. That would be 5 pi over 2 radians. Same thing as 450 degrees. And if you continue this, every time we hit either something that's coterminal with 270 degrees or coterminal with 90 degrees, you're going to end up getting an angle whose cosine is equal to 0. It's really, you notice, all the odd multiples of pi over 2. This is 1 times pi over 2, this is 3 times pi over 2, 5 times pi over 2, the next one would be 7 times pi over 2, and so on. And of course we could also go in the reverse direction. Remember, negative angles go clockwise instead of counterclockwise as we go around the unit circle. So really x could be pi over 2 or negative pi over 2, 3 pi over 2 or negative 3 pi over 2. So when x is plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2, and so on, our function will be discontinuous. One way of writing this is to say, oh, it's all the odd multiples of pi over 2. So we sometimes, in general, if you want to, you can say all the x's except, well, a general odd number can be written this way as 2n, which would be an even number if n is any integer, plus 1. So 2n plus 1, that's a general odd number where n is any integer, positive or negative, times pi over 2. At all of those values for any integer n, 2n plus 1 will be an odd number. It may be a positive odd number or a negative odd number. And we multiply by pi over 2, we get sort of this list that I wrote with dots up here. Well, let's just check that by thinking about the graph of y equal tangent x. And you may remember then that the graph of tangent x, well, it has vertical asymptotes at all the odd multiples of pi over 2, just exactly those values where we said that our function tangent x was not continuous. So that would be at pi over 2, 3 pi over 2, negative pi over 2. If I continue this graph in this direction, the next place would be negative 3 pi over 2. And just like sine x and cosine x are periodic functions, they repeat, so does the graph of tangent x, and the graph of tangent x repeats in pi long blocks. So you might remember the graph of tangent x looks something like this, and gets closer and closer to these vertical lines that I've drawn dotted in green, which are the vertical asymptotes of the tangent graph. And the tangent graph just keeps repeating in a period of pi units. So we have exactly an identical graph every pi units. And let's just look at the graph and make sure that what we're saying makes sense. Tangent x is supposed to be continuous everywhere except at these odd multiples of pi over 2. And that certainly looks to be true from our intuitive definition of continuity. We can see that we could not draw this graph through these odd multiples of pi over 2 without lifting the pen off of the paper. So that's where the breaks are occurring in the graph, and that coincides with our more careful explanation of where tangent of x is continuous. It's continuous everywhere except where cosine x is 0, and that's everywhere except at these odd multiples of pi over 2. Notice that the places where tangent x is continuous are exactly the places where tangent of x is defined. In other words, the places where tangent x is continuous are all the x values that are in the domain of tangent x. The domain of tangent x is exactly the same as the values where the denominator of this expression is 0. And so the domain of tangent x, the places where tangent of x is defined, are exactly the places where tangent of x is continuous, and the places where it's not defined right along these vertical asymptotes are the places where tangent of x is not continuous or is discontinuous. So we can use an argument similar to this for all of the other trig functions because they are all quotients of cosine and sine. For example, cosecant of x, you might remember, is equal to 1 divided by sine x. And since sine x is continuous everywhere, cosecant x will be continuous everywhere except where the denominator is 0. So cosecant x will be continuous everywhere that it is defined. Similarly, for secant x, it's 1 over cosine x, and cotangent x, which is cosine x over sine x. So all of these trig functions, including sine x and cosine x, are going to be continuous everywhere that they are defined. Or another way of saying it is that they are continuous everywhere in their domains. So I'll put everywhere in their domains. Any x that's in the domain of one of these functions is also an x where that function is continuous. Okay, the last thing that I want us to talk about are inverse functions. And so let's go ahead and think about that. Again, we're going to attack this just intuitively. It is possible to prove this in a rigorous way, but to save time, we'll just talk about it in a more informal sort of way. Suppose that I have some function f here, and I want to talk about its inverse. First of all, let me remind you that for a function to have an inverse, it has to be a one-to-one function. To be a function, it has to pass the vertical line test. To be a one-to-one function, its graph has to pass also the horizontal line test. And then you'll have a function that has a one-to-one correspondence between inputs and outputs. Every x that goes into the function has just one y that comes out of the function. Every y that comes out of the function has just one x that y came from. So I'm going to start with a one-to-one and also continuous function f. So notice that the black graph that I drew is a continuous function. Let's see what we could say about its inverse. And remember, we write the inverse of a function with a little -1 here. It does not mean the reciprocal of the function. It's kind of an unfortunate notation. It means the inverse, the function that we get when we interchange or switch the roles of x and y. Well, you might remember that the inverse of f has a graph that's the reflection of f across this line y equals x. We get the inverse function by interchanging the roles of x and y. So if, say, AB is a point on the graph of f, you might remember that BA will be a point on the graph of f inverse. So if I try to graph f inverse, there's symmetry across this line y equal x. To get the graph of f inverse, I could get it by folding my page right along this red dotted line, and the place where this black graph would hit would be the graph of the inverse function. So it would be a function that looks, let me draw the inverse in green so it's a little easier to see. F inverse would look something like this for this particular function f. So this would be the inverse of this, and if I fold the page right along the red dotted line, those two halves will match up. Well, if we suppose that f is a continuous function, and we get the graph of f inverse simply by reflecting across this line y equal x, could this green graph have some kind of a break in it, a hole in the graph, or a sudden jump in the graph? There's no way that it could. If this graph was continuous, then the green graph must also be continuous. Now that's not a proof, but it's an intuitive argument, and so what would you guess about its inverse? We would guess that f inverse is also continuous. So if I know that f is continuous, then the graph of the inverse, then its graph is a continuous line. I don't lift my pen off the paper to draw the block graph. And so the graph of the inverse would also be something that is continuous. And that does turn out to be true and can be proved rigorously. Well, what does that do for us? Let's go to the next page to see how that helps us to know that if a function is continuous, so is its inverse. Okay, so up here at the top is the fact that we just talked about on the last page. The inverse of any continuous 1-1 is just shorthand for 1 to 1. So the inverse of any continuous 1-to-1 function is, and remember we said that it is also continuous. And this has implications for our trig functions and for the exponential functions that we're going to talk about in a moment. So, for example, if we think about y equals sine x, well, first of all, let's think about y equals sine x and remember that for a function to have an inverse, it has to be 1-to-1. And if we were to graph the sine function, remember that it's a periodic function that keeps repeating, something like this, and repeats every 2 pi units along the x-axis. Is that a 1-to-1 function? Well, it's a function. It passes the vertical line test, but it is not a 1-to-1 function. Remember, a 1-to-1 function would have to have a graph that passes the horizontal line test. This does not, meaning that for a particular output value y, there's more than one input that goes to that output. So y equals sine x isn't actually a 1-to-1 function, so you might remember that to define the inverse sine function, we have to take the original sine function and restrict its domain in a way that it ends up being 1-to-1. And the usual restriction for the sine function is from minus pi over 2 to pi over 2. So we restrict the domain of the sine function and take just a little chunk of it, a chunk of the graph that will pass the horizontal line test. So we take the chunk of the sine function that just goes from minus pi over 2 to positive pi over 2. This is the y-axis, this is the x-axis, here's pi over 2. So we're just taking kind of this little piece of the graph right here, and we take the biggest piece that we can that is still a 1-to-1 function. So we just take the part from minus pi over 2 up to pi over 2. That will still have the same range as the original sine function. The y values will be between -1 and 1. Remember, y equals sine of x, and sine of any number is always a number somewhere between -1 and 1. So the y range goes from -1 on the y-axis to +1 on the y-axis. Sorry, that's a very tiny little graph there. But we restrict and just take a chunk of the graph from minus pi over 2 to pi over 2, and that way we get a 1-to-1 function. It's really not identical with the sine function where you allow x to equal any real number, but it is a 1-to-1 function. That allows us to define the inverse sine function, and the inverse of any function is always found by interchanging the roles of x and y. Essentially, you replace y with x and you replace x with y. And then you give the new function its own name, and so the new function would be y equals the inverse sine of x, or you may have seen it written as the arc sine of x. Those are just two different names that are the identical function. They're just different ones that different people use. Most of the time now we use this notation for the inverse sine notation. And remember that because the inverse function is found by interchanging the roles of x and y, that whatever was the domain of your original function becomes the range of the inverse. And whatever was the range of your original function becomes the domain of the inverse function. So what does that mean the domain of y equal inverse sine of x would be? Well, it's the same as the range of the original function. In other words, the domain of this function is all numbers x between -1 and 1. So the domain of this function is -1 less than or equal to x less than or equal to 1. And if you wanted the range of the inverse function, it would be the same as the domain of the original function. It would be all y's. I'll just jot it down here. The range would be all y's between minus pi over 2 and pi over 2. And if you were to graph the inverse function, I'll try to graph it just a little bit larger than I did the sine function, but it looks like the reflection of this graph across the line y equals x, that line at 45 degrees. The domain is from -1 to 1, and the range is from minus pi over 2 to positive pi over 2. And let's see, it looks like the inverse of this, so it looks roughly like this. It's a very rough graph of it. And what we're saying then is that since y equals sine x, defined just on the interval from minus pi over 2 to pi over 2, is a continuous one-to-one function, its inverse is also a continuous function. So the inverse sine function, y equal inverse sine of x, is supposed to be continuous on its domain from -1 to 1. And I can certainly see that if I look at this little chunk of graph, it does appear graphically to be a continuous function. There are no breaks or holes in the graph or vertical asymptotes or things like that. Well, what can we say in summary then about not the trig functions, but about the inverse trig functions? Because all of the trig functions are continuous everywhere in their domains, it means that the inverse trig functions, along with the restrictions needed to make them one-to-one, are also continuous everywhere on their domains, or everywhere that they are defined. So I'm going to put down that the inverse trig functions are continuous everywhere they are defined. Or another way of saying it is everywhere on their domains. Everywhere on their domains. So if the inverse trig function is defined at a particular value of x, it's also continuous at that value of x. Okay, let's go ahead and think now about exponential functions. Remember, an exponential function is a function of the form f of x equals a to the x, where a is some fixed real number. So keep in mind here that a is a constant. An example of an exponential function would be something like y equal 2 to the x. The base is a constant, and notice that the exponent is where our variable appears. So y equal 2 to the x, y equal 3 to the x, y equal 10.4 to the x. So a has to be a constant. And also I might mention that a needs to be a positive constant. So a is some value that's greater than 0. Okay, here I've graphed y equals a to the x. I've actually only graphed it for values of x, values of the input here that are rational numbers. Remember, a rational number is something that can be expressed as a over b, where a and b are both integer values. And when we first define the expression a to the x, we really define it only for x being a rational number. However, in an earlier section in our textbook, they go ahead and extend the definition of a to the x to include x's that are irrational numbers, so that you defined it for a to the x, where x is any real number, real numbers being rational plus irrational numbers put together. And we extend the definition of a to the x for all of the points that would be in between these rationals by saying that if we want a to some irrational number, we will define the output a to that irrational number as the exact output that we need so that this function is always increasing. Well, it turns out that means that when we write y equals a to the x and x can be any real number, that we end up getting not only a function that's always increasing, but a function that is continuous. So we're going to go ahead then and just say, well, because of the way that we define a to the x, where x is any real number, the method that we used for defining it automatically makes this exponential function a continuous function. So f of x equal a to the x is continuous everywhere that it's defined. And where is it defined? Well, for an exponential function, you can plug in any real number. X can be a positive number, x can be 0, or x can be a negative number. If I look at something like 2 to the negative 3, that has a definition. It's 1 over 2 to the 3, or 1/8. So I can plug any real number that I want to in here, and my function will be defined. So it's continuous on its domain. I'll say on its domain, but its domain is all real numbers. So I'll say on its domain, namely the interval from minus infinity to infinity. So that's the domain of a to the x. We will actually also need the range for what we're going to talk about next. So what's the range of an exponential function like this? Well, the range is the set of output values, and you notice this whole graph, this purple graph that I've drawn, lies above the x-axis. In other words, if I pick any point on this graph, when I go up to that point and over, I will hit a positive value on the y-axis. So the y-coordinates of points on this graph are all greater than 0. Another way to think about it is to think about something like 2 to the x. Even if I plug in a negative value, such as negative 3 for x, 2 to the negative 3 is 1 over 2 cubed, which is the number 1/8. And you notice that that's something that is positive. So a to the x is always going to be a positive value. Remember, a is a constant, and at the beginning of this discussion I mentioned that a has to be a positive number greater than 0. So the range is all y's greater than 0. The range would be the interval from 0 to infinity, or y between 0 and positive infinity. Okay, well, we've just gone ahead and basically stated that exponential functions, because of the way we define them, are continuous on the whole real number line. They are everywhere continuous, just like a polynomial is everywhere continuous. What about logarithmic functions? Well, remember that log base a of x is really the inverse of the exponential function a to the x. So when I write f of x equals a to the x, its inverse function is the log base a of x function. And we're not going to go through and review log functions here. They were reviewed in an earlier, I think in chapter 1 of your textbook. So let's think about this. Well, here's the graph of a to the x. We know that log base a of x is the inverse of that function. If I were to draw the graph of log base a of x, the inverse of this purple graph here, I would get it by again reflecting across the line y equal x, just like we did with earlier inverse functions. And if a point AB is on the graph of this, the point BA will be on the graph of the inverse. And if you thought about maybe putting blue ink right on top of this purple graph and folding the page right along this diagonal dotted line, you would get a new graph that looks something like this. And this would be the graph of the inverse, f inverse of x, which is log base a of x. And what did we say up here at the top? We said that the inverse of any continuous one-to-one function is also continuous, And a to the x is not only a continuous function, it's also a one-to-one function. It passes the horizontal line test. So its inverse, log base a of x, must also be a continuous function, at least on its domain. So what we could say then is that the inverse function, log base a of x, is also continuous on its domain. And what is the domain of log base a of x? Well, I'll say namely, remember that the domain of the inverse function is the same as the range of the original function. And that again is because the inverse function is found by interchanging the roles of x and y. So whatever was the domain of the original function becomes the range of the inverse. And what we're really interested in is the range of the original function becomes the domain of the inverse. So log base a of x is also continuous on its domain, namely, and its domain would be this interval. Instead of being all y's between 0 and infinity, it would be all x's between 0 and infinity, but in interval notation it looks identical to the way that we wrote the range of the original function. So the log base a of x function is continuous everywhere on its domain, and its domain is the set of all x values between 0 and infinity, not including 0 itself. And just a little note about the domain of a log function. Remember, when you talk about log base a of some x value here, this x does have to be in this interval for log base a of x to be defined. You can see it from the graph. There's no portion of the blue graph that extends to the left of x equals 0. There are only points on this blue graph that have x coordinates that are larger than 0. So the x that you plug into a log function, you may remember from pre-calculus, has to be a positive number. You can't take the log of 0 and you can't take the log of a negative number. Okay, let's go ahead and turn to the next page. What we're going to do next is just to summarize everything that we've said about these particular kinds of functions that we've looked at. So let's summarize here. The following types of functions are continuous at every number at which they are defined. Or another way of saying the same thing, they are continuous at every number in their domains. And let's just list the kinds of functions we've talked about. We've talked about a number of different functions, for example, polynomials. And they will be continuous at every number at which they are defined. And what numbers are those? Just remember, for polynomials, they are defined everywhere from minus infinity to infinity, so they are continuous everywhere from minus infinity to infinity. We say they are everywhere continuous. The next special type of function we talked about were rational functions. They are also continuous everywhere on their domains, and remember, for rational functions, it's everywhere that the denominator is not equal to 0. So everywhere the denominator does not equal 0. So they're continuous at every x value except x values that make their denominator 0. We talked about root functions, and it could be square roots, cube roots, tenth roots, whatever. They are also continuous everywhere that they are defined. For an odd root, that would be all real numbers, because we can take an odd root, such as a cube root, of both a positive and a negative number, as well as 0. For even roots, we have to worry about the x values that would make what's under the root symbol something that is not negative, and we'd have to throw out any x values that make what's under the root negative. So polynomials, rational functions, root functions, those were the first ones we looked at. Then we talked about trig functions, and they are also continuous everywhere on their domains. Remember that for cosine x and sine x, those are actually continuous on the whole real number line from minus infinity to infinity, and the other four trig functions are ratios of those, and they are continuous everywhere except where the function in the denominator would end up being 0. Now we've already talked about inverse trig functions, and the inverse trig functions are also continuous everywhere on their domains. So everywhere that they are defined. And the last two types of functions we talked about are exponential functions, things like e to the x, 2 to the x, in general functions of the form a to the x, where a is some positive constant. And those are continuous everywhere on their domains, but again, their domains are from minus infinity to infinity, so they're actually everywhere continuous. And then we talked about their inverses, the log base a of x. That would include things like the inverse of e to the x, which is ln of x, the natural log function. But in general, log base a of x is again continuous everywhere on its domain, and log base a of x has a domain of, in interval notation, it would be the interval from 0 to infinity. So that's where the log functions are continuous. So that's a quick summary of all the specific kinds of functions that we've looked at. And I just want to mention again that, remember, we had that more general theorem that said that if we know that f and g are any of these above types of functions, then from that earlier theorem we know that f plus g, f minus g, a constant times f times g, and f over g are also all continuous on their domains. So if we have any combination of these kinds of functions that are added or subtracted or multiplied or divided, to figure out where they are continuous, all we really have to do is figure out what their domains are. Well, let's go ahead and do just a few examples